All right, so you might be looking at this page thinking, I feel like we've done this before. Well, we have. But now we're focusing on kind of the nitty-gritty details. We want to look at the details, okay? And we haven't done this at least on an assessment in this exact way. We're going to talk about what a true sign analysis should look like, where we're analyzing the function f itself to see where it's increasing and decreasing. Most of the time we've done this with the derivative. So, just a reminder about what it means for a function to be increasing or decreasing. It is increasing on an interval if for any two numbers x1 and x1 is less than x2 implies that f of x1 is less than f of x2. So if the next function value is bigger than the previous function value, or decreasing means that the next function value is smaller than the previous function value. So how does this relate to the derivative? Well, we've already talked about the fact that increasing has to do with the derivative being positive and decreasing derivative being negative, and constant is being when the derivative is equal to 0. But this is the official definition here, and we're going to talk for a second here on the endpoints being included. And so this says if f prime of x is greater than 0, for all x in an interval, then it's increasing up until the endpoints, or decreasing up until the endpoints. So for those of you that doubted me in the past, if we have the graph of a derivative, and it looks like this. And let's say this is 5, and this is 3, and this is our graph of our derivative. So technically, f prime is less than 0 from negative infinity to 3 and from 3 to 5, okay? But when we talk about decreasing, we say that f is decreasing all the way from negative infinity to 5. We don't worry about that 0 because of this right here. So if f prime is less than 0 on negative infinity to 3, then that means that f is decreasing on negative infinity to 3 included. And if f prime is less than 0 on 3 to 5, that means f is decreasing on 3 to 5 included. So that would mean that f is really decreasing at the moment 3, right? F is decreasing on negative infinity to 5 included. On the AP test, they don't really worry about the endpoints, whether you put a bracket or a parentheses, but it technically would be a bracket there. But the important part that really, really matters is that it is decreasing for that whole time. Okay, so now let's just talk about a couple of words that we haven't used before. One is a critical number. A critical number is any place where f prime is equal to 0, or if f is not differentiable. So f prime does not exist. Okay, we haven't really talked about these situations very much, and so these are going to matter a lot more, these critical numbers. And so we've already talked about a question like this first example here, where we're looking to find an interval where f is increasing or decreasing, and they show us the graph of the derivative. So this is f prime of x. And so we've already looked at a problem like this, so let's just do a refresher. So if this is f prime of x, then f prime is negative during these times. So f is decreasing on negative infinity to 0. Technically closed, but usually I'm a little lazy and I do open. And 2 to 4. Okay. And then f is increasing on, and that is because, this last one is because f prime is less than 0 on those intervals, right? And then f is increasing from 0 to 2 and 4 to infinity. Because f prime is greater than 0. So we've already done problems like this. We've even been assessed over this, okay? But now we're going to talk about how do we analyze or do a sign analysis with doing all the correct details for a free response question, because these are usually free response questions, in order to find where a function is increasing and decreasing. And specifically, most of the time you're given f here. This also works when you're given f prime, but most of these examples is when you're given f. So the first thing you're going to do is find the critical numbers. So that's when f prime equals 0 or f prime does not exist. And the second part we haven't really talked much about until now. You're going to determine the sign of f prime by picking a test value in each of these intervals, because you want to test values between all of your critical numbers. And then you'll use the theorem to decide if it's increasing or decreasing in those intervals. Okay, so let's see an example. And these are important to know exactly what good quality calculus work looks like, which is why we're taking a little bit of time to do this, even though it's kind of review. So first thing to determine when f is increasing or decreasing is to find where f prime equals 0 or f prime does not exist, because these are our critical numbers. So we're going to take the derivative. So here that'll be 3x squared minus 3x. We will look for where it does not equal 0 or where it does not exist. So f prime of x equaling 0, we'll just rewrite it here. Actually, let's give us some more spacing over here. We'll have to factor out a GCF, 3x. That'll leave us with x minus 1. And so it will be when x is 0 and x is equal to 1. So these are our critical numbers. But we also need to look for critical numbers where f prime does not exist. But is there anywhere where this equation does not exist? No, there's no zeros in the denominator, there's no logarithms, there's no square roots that could be negative. So this part is never. So there's no critical points from the f prime not existing. These are our only critical points. So now we're going to use this to create sets of intervals that we're going to test. And this is where you could use a little picture if it helps you, but this is never going to count as work, so just be careful. But we're going to test 3 intervals here to see whether f prime is positive, negative, in between, right? Because it's 0 at these moments. If we're talking about f prime, it is 0 at 0 and 1. And so we want to know, is it positive or negative in between 0 and 1? What about bigger than 1? And what about less than 1? So we have 3 intervals here. So we're going to test a value in each of those intervals. So let's pick a number in this interval here, below 0. So anything less than 0. So let's pick, I don't know, -1. Now, you don't actually have to find that value. You can if you want to, but sometimes you might not be able to find it without a calculator. So you have to at least be able to analyze the derivative. So now remember, this derivative here is the same thing as 3x times x minus 1. So when we analyze this, it's usually easier to analyze it in the factored form. Because if we plug in -1 for this first x here, you know that's going to be a negative number. 3 times -1 will be specifically -3, but you definitely know that's a negative number. And then if you plug in -1 here for the second part, you're going to get -2. So that's also a negative number. So again, you don't really need to know exactly what the numbers are. If you want to, you can find it if you can. But you do need to know whether it's positive or negative. When we multiply a negative times a negative, that's going to be a positive. So this is what we call a sign analysis. So we know from 0 to -infinity, f prime is going to be positive for this whole time here. Right? All this time, because it's only 0 at 0, right? So before it can't change signs again. So it's going to be positive for that whole time because we tested one value less than 0. So now let's test a value between 0 and 1. So let's test f prime of 0.5 or 1/2. You can find the exact value if you want, and if that's possible, but we need to at least analyze whether it's positive or negative. So plug 0.5 into 3x, and you're going to give it a positive. Plug 0.5 into x minus 1, the second part, and you're going to get a negative. So that'll be a positive times a negative, which will be a negative. So that tells us that the derivative is negative between 0 and 1 for that whole time. And then we need to test one value bigger than 1. Plug in that to 3x and you get a positive. Plug in 1 into 1 minus, or sorry, bigger than 1, not 1. We know already 1 is at 1 and 0. So let's do 2. Plug in 2 into 3x, you'll get 6, but specifically you'll get a positive. Plug in 2 into x minus 1 and you'll get 1. So a positive times a positive will be a positive. So from 1 until forever, the derivative will be positive. So this tells us that, I'll write my answer here, f is increasing whenever the derivative is positive, right? So from negative infinity to 0, that whole interval, and from 1 to infinity, that whole interval, f is increasing because f prime is greater than 0 that whole time because we tested that whole interval. And then f is decreasing on the interval 0 to 1 because f prime is less than 0. So this is what we call a sign analysis. And when you're doing this on a free response question or on a test, you have to show that you've tested values, okay? This sign chart here is not going to give you any work, right? So you have to show that you've set the derivative equal to 0 and tested where it does not exist, and you have to show that you've plugged values into the derivative. Now, you don't have to show exact what values you get out, but you have to show that you're figuring out if it's positive or negative. You can jump straight to plus, minus, and plus, but I'll do the in-between part. So now we're just going to do 3 examples together, and then we'll be done, and you can practice this for homework. So first thing first, we want to determine the intervals on which f is increasing and decreasing, and perform the analysis on all values from negative infinity to infinity. Okay, unless otherwise. And then we want to provide justification. So this is justification, the wording, and we're supporting our justification with our analysis. So first, we're going to look for where f prime equals 0 or does not exist. Find our critical points. So we need f prime of x. So it'll be 15x to the 4th minus 15x squared. And we want to know where f prime equals 0 and where f prime does not exist. Well, this guy exists everywhere. It's a polynomial, so we don't have to worry about that at all. It's never. And so now we just need to find where f prime equals 0. So we'll take 15x to the 4th minus 15x squared. Set it equal to 0. We'll factor out 15x squared. That'll leave us with x squared minus 1. So this will be 15x squared times x minus 1, x plus 1. So where the derivative of 0 is 0, negative 1, and 1. Okay, those are our critical points. Okay. And so then we need to test all the intervals around these points. So if you want to draw yourself a little picture just to help you visualize, you can. But remember, this won't count as credit. So we'll have between negative 1 and 0, we'll need to test the interval less than negative 1, between negative 1 and 0, between 0 and 1, and greater than 1. And we'll need to see what the derivative is doing. So we need to pick a value in each of these sections and plug them into the derivative to test all 4 intervals. So let's start with something less than negative 1. So we'll start with negative 2. And again, it can be helpful to plug it into this form of the derivative so that you're seeing what happens. So if I plug it in there, 15x squared will give me a positive. Plug in negative 2 into this one, and you'll get a negative. And plug negative 2 into x plus 1, and you'll get a negative. So that'll be a positive times a negative, which will be a positive. So if we're looking at f prime and we want to put it on our chart, we know that it's positive less than negative 1. Okay, so now let's pick a number between negative 1 and 0 and see what happens. So let's pick negative 1/2. If we plug in negative 1/2 to 15x squared, we'll get a positive. Plug in negative 1/2 to x minus 1, we'll get a negative. Plug in negative 1/2 into x plus 1, we'll get a positive. So this will be negative, positive, negative. We'll multiply together to be a negative. Again, you could find the exact value, but that's a lot of math. And all we need is it positive or negative? So we know f prime will be negative in the region between negative 1 and 0. Let's test a value between 0 and 1 next. So we'll pick 1/2. Plug it into the derivative, 15x squared, that'll be positive. 1/2 minus 1 will be negative. 1/2 plus 1 will be positive. So this will also be a negative. So it's negative between 0 and 1. And then we need to test a value bigger than 1, so let's pick 2. So 15x squared will be positive, 2 minus 1 will be positive, and 2 plus 1 will be positive. So this is going to be a positive. So it's positive from 1 to infinity. So then we already know our intervals, so we can just state that f is decreasing. And it'll be decreasing all the way from negative 1 to 1, even though it hits 0 at this moment right here. F is defined at that point, so the function goes right through that point, and so we don't need to break it up. In fact, we don't want to break it up because f prime is less than 0. Technically, we would say between negative 1 and 0 and 0 and 1, but we can just say that. And then f is, like, you could add because on negative 1 to 0 and 0 to 1, but we kind of are allowed to just leave that out and pretend like we know we're already saying that. F is increasing on negative infinity to negative 1 and 1 to infinity, those two intervals, because f prime is greater than 0. All right, let's just do a couple other analyses where we might have some weird things happen. So this one here is mostly weird just because it's trigonometry, so we're going to do this one together, and then the last one has some weird stuff happen. So here, we'll start by finding where the derivative equals 0 or does not exist. So we'll start with finding the derivative. That'll be 1/2. Derivative of sine is cosine. And we're only worrying about the interval from 0 to 2 pi. Otherwise, this function would have a lot of zeros. So we're just focusing in on that. So we want to know where f prime equals 0 or f prime does not exist. Cosine is a continuous function. It does not have any undefined values. So this is never. We don't have to worry about that. But we do have some places where this will be 0. So 1/2 minus cosine x equals 0. We'll add cosine to the other side. And we'll have 1/2 equals cosine x. Now we need to use our unit circle to figure out where cosine is equal to 1/2. Remember, cosine is the x value. So we're going to be looking at the x value of 1/2. So that'll be these two angles where cosine is equal to 1/2. So that'll be the second of the pi over 6 angles here. So up here, this will be pi over 3 is where cosine is 1/2. And then down here at, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Oh, I missed the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi over 6, which simplifies down to 5 pi over 3. Okay, so this is going to be at x equals pi over 3 and 5 pi over 3. We don't have to worry about after 0 and 2 pi because we're only doing one revolution of the unit circle. Okay, but there are two places where the x value is 1/2, both of those angles. Okay, and there's nowhere where the derivative does not exist, so now we just need to look at what intervals we need to test. So we need to test less than pi over 3, we need to test between pi over 3 and 5 pi over 3, and we need to test something greater than 5 pi over 3, because we know the derivative is 0 at both of these, and we need to test the intervals in between. So let's start with something less than pi over 3. So let's just do 0. That's an easy one on the unit circle, because that will be less than pi over 3. And plug in 0, or wait, maybe not 0, because we're not supposed to include that. Okay, I don't think it's going to make a difference for this one, but let's do pi over 6 instead. That's still an easy one on the unit circle. It won't affect our intervals. So let's see. F prime of pi over 6. Remember, f prime is 1/2 minus cosine of x, so that'll be 1/2 minus, and cosine at pi over 6 is, let's do another unit circle over here. Cosine at pi over 6 is your x value right here, so that's square root of 3 over 2, which is bigger than 1/2. So it'll be 1/2 minus square root of 3 over 2, and square root of 3 over 2 is bigger. So this will be a negative number. So we'll have a negative derivative when we're less than pi over 3. Now let's test something between pi over 3 and 5 pi over 3. So let's do pi. That'll be a nice value, because remember, pi over 3 is up here and 5 pi over 3 is down here. So pi will be a nice one to plug in. So f prime of pi, that'll be 1/2 minus 0, no, minus -1. At pi, cosine is -1, so it'll be a positive number. And then let's do f prime, so it's positive in here. And now let's test a number bigger than 5 pi over 3. So let's test like 11 pi over 6. That's this one right here. So we tested those three values. So let's test f prime of 11 pi over 6. So we'll have 1/2. Cosine of 11 pi over 6 is also square root of 3 over 2, which is bigger than 1/2. So this will be a negative. So it'll be negative again after 5 pi over 3. So because we're only worried about from 0 to 2 pi, we're really stopping here at 0 and stopping here at 2 pi. All right, so when we say when f is increasing, it's going to be when the derivative is positive. So from pi over 3 to 5 pi over 3. Because f prime is greater than 0. And f is decreasing because, or not because yet, on 0 to pi over 3, because we're stopping at 0, and 5 pi over 3 to 2 pi, because f prime is less than 0. Okay, so now one more example where some weird stuff happens. That last example was not weird, besides the fact that it was trigonometry. All right, so here we're going to see where the derivative is equal to 0 or does not exist, so we need the derivative. We'll have to use the chain rule here. We'll do low d high minus high, not chain rule, I said chain rule, I meant quotient rule, that's what I'm doing. Low d high minus high d low, all over the square of what's below. And let's simplify this down, because we're not going to be able to analyze this derivative unless it's simplified. So we'll get 4x to the 5th minus 2x to the 5th minus 2x, or 2x to the 5th minus 2x all over x to the 4th. Pull out a common factor of x. That will cancel out with the denominator. So we have f prime of x will be equal to 2x to the 4th minus 2 all over x to the 3rd. So it's important to make sure you simplify all the way. This is why we practice this. Ooh, we can even factor out a 2. Because you're going to have to analyze this derivative. So this is why we practice simplifying derivatives when we are done. Okay, so now we need to know where f prime is equal to 0 or f prime does not exist. Well, for the first time, we do have a point where f prime does not exist. That's going to be whenever the denominator is 0. We never had a denominator before, but here we do. So we have to set the denominator equal to 0, which here that's pretty obvious. That's just x equals 0, right? In other cases, you might have something more complicated when you set the denominator equal to 0. And then f prime will be equaling to 0 when the top equals 0. Sorry, I said I was going to simplify that, and then I wrote that as a 2. Set this equal to 0, so it'll be x to the 4th minus 1 equals 0. X to 4th equals 1. So x will be equal to plus or minus 1. When you take the 4th root of 1, you'll get plus or minus 1. So we have 3 critical numbers here. Well, it seems like we have 3 critical numbers. I'm going to tell you that one of them is not here in a second. It seems like we have 3 critical numbers, 1, -1, and 0. But 0 is actually not a critical number because the function does not exist at this point. So if you go back to our definition on the other page, something we didn't pay super duper attention to, it says, let f be defined at c, right? So the function has to exist at a point in order for it to be a critical number, right? It has to be a point on the function. So although the derivative does not exist here on this example, sorry, I lost my camera here for a second. Gotta figure out where it is. Okay. Come back, example 5. All right. Here is example 5 again. So although the derivative does not exist at x equals 0, if you plug x equals 0 into the original function, f of 0 does not exist. So that is not a point on our function. We're going to have a vertical asymptote there. So this is not a critical number. Okay. Now, we will still use it to analyze our intervals of increasing and decreasing because f could change there, but it is not a critical number. So we'll still use it when we go to test our intervals here, but technically that is not a critical number. It's just -1 and 1. So we still want to use that because it could still change from increasing to decreasing around a vertical asymptote. So we still want to use that as a breaking point in checking our intervals, but it's not a critical number, which will matter more in the next unit Monday, whatever next day is this class. So now let's test some values in these 4 sections. So we're going to test the derivative at, let's try -2. So we're now looking at this derivative at -2. If I plug in -2 and I bring it to the 4th power, I'll definitely get a positive number out of that -1. So that'll be a positive in the top. And then when I cube it, though, I'll get a negative in the bottom. So this will be a negative number. F prime, something between -1 and 0. Let's do -1/2. Plug that into x to the 4th, and that's actually going to become like a really small number. Subtract 1 It's going to be positive, but it's going to be way smaller than 1. So we'll have 2 times a negative over a negative when you cube it. So that will be a positive number. F prime, so we have negative, positive. Now we'll try 1/2. So plugging 1/2 into x to the 4, same thing. That's going to get even smaller than 1. It's going to make 1/2 an even smaller fraction. So -1, that'll be negative. So 2 times a negative. But now 1/2 to the 3rd will give you a positive in the bottom. So this will be a negative. And then f prime of something bigger than 1. Oh, so negative here. Something bigger than 1 will be 2. And when we raise 2 to the 4th power, subtract 1, that'll definitely be a positive times 2, and then x cubed in the bottom will be a positive. So now we'll have a positive number. So when it's still, so the fact that the function is undefined at 0 is still going to break up this interval, right? It's changing from positive to negative at 0, but it's not a critical point because it's not a point on the function. There's a vertical asymptote there. So the function is like doing like this, right? So it can't be a critical point if it's not a point on the function, which will matter a little bit more next time. Okay, so f is increasing from -1 to 0 and 1 to infinity because f prime is greater than 0 and f is decreasing on -infinity to -1 and 0 to 1 because f prime is less than 0. All right, that is all.